torque on a current loop. Now we have a current loop in a magnetic field. This loop we have, this is counterclockwise current. Okay, and this loop we will find out. Okay, it will be, you have a current, you will find it has a torque on this loop. First, we define the torque acting on the current loops. We define the direction of the current loops. N. Remember, they call it current direction of the current loop by a right-hand rule. We use a normal vector n that is perpendicular to the plane, okay, plane of the loop. So, the first step, we point or curl our fingers, your right hand, in the direction of the current at any point on the loop. This one. Use your right hand. Curl your finger, 4 fingers. And your extended thumb then points in the direction of the normal vector n. We define it. In this case, you use your right hand, you get n is up. This n we call the direction of the loop. Okay? Unit. In our case. Now let's analyze this. This is loop. This is a magnetic field goes this direction. Let's analyze how much is the loop. We have a current in this loop. It's clockwise. Okay. Now we analyze side 2 and side 4. This is 1, 2, 3, 4. Okay. Side 2, 4. Now we look at this graph. We look at from this side. So this page, this line is this line. Okay, we take a picture of this line. We use right hand loop. Okay, this current loop. So this is the direction of the loop n. Okay, this is the same thing. This is the n. This is the direction. Okay, now let's analyze it. First, we look at these F2 and 4. Okay. We know FB equal to IL cross B. This is the length of L. F2 and F4, they are the same. What is I current. Length, this is called a B. Okay? And the angle, because this is angle with the current, this angle is 90 degrees minus theta. Okay? And F4, you have the same situation, a different direction. Okay, they are equal and they are in the same line, so they cancel out as a total. No net force acting on this loop by F2 and F4. Okay, and then if we F1 and F3, F1 and F3, they are perpendicular to the curve, right? Look at this one. Look at this one. They're perpendicular to N, to B. Okay, to B. So this, the magnitude is I, the length is A, the B, the angle is 90 degrees sine 1. They are equal and opposite, but wait. You see this one? This is F1, this is F3. They don't acting on the same line. So let's see what's happening. Okay. Even though they have the same magnitude, but they didn't in general on the same line. So let's see the torque around this point, axis, rotation axis. We know this F1 torque equal R cross B. This R is this one. Okay, the F is this one. Okay, so with the torque around this one, F1 is F times this one. What is this one? This one is half of this. This is B, half B. And this angle is equal to this angle theta. So this length is half B sine theta. So this torque equal to 2 parts. One part from F1. This F1 is IAB. Multiply by this, half B sine theta. The same thing for F3 is IBT plus half sine theta. So this pair, you have a torque acting on this loop. Put together, we get it. IAB sine theta. This AB is the area of this loop. So we call this A. Okay? So the torque can be right in general as IA cross B. B theta is this angle because we know that this is N, the direction of A. The A has the magnitude AB, the area, and direction perpendicular to this one, the N. So torque on this current loop is IA cross B. There's A defined as area and normal direction. If you have N term, then the torque is multiplied by N, NA cross B.
This square aluminum frame rotates on a pivot bearing. At the bottom of the frame, contacts dip down into two separate pools of mercury, which allow us to run current through the frame, yet leave it free to rotate. We'll run a current in this direction through the frame, then bring a bar magnet up to the frame, north pole first. The frame rotates to the right. If we repeat with the south side of the magnet, the frame rotates to the left. This is a large open model of an ammeter movement. The large permanent magnets on either side provide the magnetic field. Current applied to the meter flows through this central coil, which rotates by an amount that is proportional to the current. When we reverse the direction of the current, the deflection reverses.
This is a large working model of a DC motor. Permanent magnets on the side provide an external magnetic field. Current to the central coil flows in through this commutator, which reverses the direction of the current through the coil twice per rotation. When current is fed into the motor, it begins to spin. This animation shows the current that runs through the coil as it turns and the magnetic forces that act on the current.